All right, we'll go ahead and get into this next section of notes here. So this is going to be 8.3, and we're talking about parallel lines and proportional parts. Okay, so date today is either the 19th or 20th, depending on what hour you have this class. And our objective for today is we're still using similarity and setting up proportions, but specifically we're really focusing in on what if I just had one triangle and I had proportional parts in that triangle. Okay, could I use that to set up some different problems and solve for some different lengths here? Okay, so first off, theorem that we're going to need to use that's going to help us here is what we call the triangle proportionality theorem. Okay, the triangle proportionality theorem. And it says this, it says if a line inside a triangle is proportional, oops, sorry. Let me try that one more time. If a line inside a triangle, let me switch this up, is parallel to one of the sides. There we go. Okay, if a line inside a triangle is parallel to one of the sides, then what I can say is then it divides the remaining sides, or the other sides, into proportional parts. Okay, if a line inside a triangle is parallel to one of the sides, then it divides the remaining sides into proportional parts. Okay, and this is one of these theorems where it's definitely easier to see an example of this than just read through the definition, because I know that's pretty math vocab heavy. Okay, so first off, we just need a triangle here, so it doesn't matter what it looks like. Let's just say we have this triangle here. We'll draw this. Okay, 3 different sides. And it's saying, what if I had a line inside the triangle that's parallel to one of the sides? So for example, let's use this here. Let's say these 2 lines are parallel. Okay, and I'm going to go ahead and label everything in this triangle as well. So let's say, for instance, A, B, and C. And then let's label the intersection points here, D and E. If this is the case, what it's saying is it's taking these remaining 2 sides here, this one and this one here, and it's dividing them into proportional parts. So what I can say here is I can say AD, part of that side, over the rest of that side, DB, is always going to equal the same thing as the other side over here, AE, over the remaining piece, EC here. Okay, this is what the triangle proportionality theorem means. So in other words, if you see a parallel line inside a triangle, you want to look for the different pieces, and you're always going to be able to set up a proportion with those. Okay, so putting this to use here, making sure we understand how this works. Okay, if you need to, you can sketch this diagram here. Let's say we have this picture, and let's say we're told PS is 12.5, SR is 5, and then PT is 15. Okay, and saying if that's the case, I want to find the side length of TQ. So first off, I'm going to go ahead and label all that information that I was given here. I was told 12.5, SR is 5 here, and then PT is 15. Okay, and you want to find TQ, so in this case, we can just label that X. Okay, and so we're going to use exactly what we just wrote down on that example here. I can set up 2 proportions because I see that these 2 lines here are parallel to each other. So for example, we can say 12.5 over the rest of that side, so 5 here, equals the same thing as 15 over X. Okay, so this is how you need to set up your proportion. Always using the little pieces. Don't worry about the total lengths. We'll use those later. Okay, and now if I want to solve this proportion, we've talked about multiple ways to do this. One of the ways that we've talked about that's always going to work is cross multiplication here. So I can go ahead and cross multiply. Okay, because it's going to be hard to find a number to multiply 12.5 by to get to 15. So we cross multiply here. The first 2 values are just 12.5 and X. So 12.5 times X is just 12.5X. And on the other side here, I'll just write this out just so we can see it. That's just 5 times 15 is what we're going to do. Okay, so again, simplify 12.5X here equals 5 times 15. We can type this into our calculator if we didn't know, but that's just going to be 75. And then last step here, divide by 12.5. And again, if you need to, you could use your calculator, but this is actually a good mental math practice. I know 12.5, if I double that, it's going to be 25. So I can use that information and figure out how many times 25 goes into 75. and then double it. So in this case, in any case, however you figure it out, it's going to be x equals 6 here as your final answer, okay? And then again, always good to double check. Do I need to plug this back in for anything? In this case, it was asking for TQ, and we already labeled that x, so we just found TQ is 6 here, okay? In other words, okay? So this is how we set up these proportions, okay? Pieces over one another, okay? Another way that we can use this is we also have the converse of this theorem, okay? The converse of this theorem. And we've talked about this idea before. The converse is just when I take the hypothesis and the conclusion of a statement and I swap the places of them. So in this case, we're going to say if a line inside a triangle divides the sides, or let's say divides two sides into proportional parts. If I look and I just see a line here and I see that it divides the sides into proportional parts, then what I can say is I can say then the line is parallel to the third side. Okay, so since it's the converse, it's the exact same idea that we just mentioned. We're still looking for parallel lines and proportional parts. We're just switching the order of them. Okay, so for example here, again, let's draw a triangle. Doesn't matter what it looks like. Draw a triangle here. And let's draw a line inside the triangle. And notice in this case, we're not going to say that it's parallel from the start. Okay, that's what we would be able to figure out if we were given the side lengths. So for instance, here we could choose some different side lengths. Let's say we have maybe side lengths of 2 and 3 over here. And then maybe let's go 6 and 4. Okay, and it's saying if this is the case, if these sides are proportional, again, I could label this if I'd like to, but I'm going to say if 3 over 2 equals 6 over 4, which it does, they would come out to be the same proportion, they're both 3 halves, then I could say those two lines are parallel here. So for instance, let's just label this x, y, z, and then maybe VW, doesn't really matter. Okay, we're saying if this is the case, then I would be able to say that VW is parallel to YZ. So using the same kind of theorem, just in the reverse order, or our conclusion just comes out to be different. But the work itself is still the same. Okay, so practicing this a little bit, making sure we understand what this means, or how I would use this in an example here. Let's say we have example 2, where we have this triangle here. We're told EH has a length of 3, HF has a length of 9, and then we're just told that DG is 3/4 the length of GF. And it's asking the question, is GH parallel to DE here? Okay, so again, just like we did in the last one, I'm going to go ahead and label the information that I'm given here. So EH is 3, HF is 9, and in DG, we're not really told what the length is. We're just told it's 3/4 the length of GF. Okay. And remember, it's saying if I want to show if these lines are parallel, I need to see if these side lengths are proportional. So in other words, if they were parallel, then I would need to say, or need to know, that EH over HF, okay, those two pieces here, would have to be the same thing with the other side, DG and GF here. DG and GF. Okay? So let's set these two fractions up and see if that's going to come out to be the same or not. So for example here, if we have this, EH we already know is 3, and then HF is 9. Okay, and so if I want to simplify this fraction, 3 over 9, that's the same thing as 1/3. Okay, so this is, in other words, kind of like the scale factor or the difference between the two. Okay, EH is 1/3 the size of HF. Okay, and now with DG and GF, like I said, we weren't told what the lengths are, but we were told that that fraction or that proportion that's going to come out is going to be 3/4. So for a simple example, if we wanted to choose side lengths, we could say GF is 4, and then DG is just 3/4 of that, so DG could just be 3. Okay, that's just one example. In any case, your fraction comes out to be this. It comes out to be 3/4. Okay, so you have this here, 1/3 and 3/4. Okay, these are not similar, or these are not the same. So because of that, are these two lines parallel? I would say no, the lines are not parallel. Okay, in order for them to be parallel, those lines would have to be, or those sides, excuse me, would have to be proportional. Okay, so that's how we use it. It's still setting up proportions. It's just being able to tell whether lines or sides are parallel or not. Okay, so that is some of the basics of what we're going to do. And then one other thing that we need to add in here today as well is talking about what a midsegment of a triangle is, because we also have ways that we can set up proportions with these here. Okay, so the midsegment of a triangle, just to start, okay, this definition is a line inside a triangle, that connects two midpoints of different sides. Okay, midsegment of a triangle is just a line inside a triangle that connects two midpoints of different side lengths. So for example, what this would look like here, if I go ahead and draw a triangle, let's just call this JKL. Okay, all I would need to do to find a midsegment here is I would need the midpoint of these sides. So for example, let's say JK, the midpoint of that is roughly right here. Okay, it might not be exact, but let's just say that's where it is. Okay, and then same thing with KL here. Let's say the midpoint's about right here. Okay, and we'll name these M and N. So your midsegment here would be a line that connects those two, okay, M and N. Okay, and then notice as well, you could also have a midpoint of your last side as well. So maybe we call that O. And so if I want to connect midpoints, I could also connect this. This would also be a midsegment, and then this would also be a midsegment here as well. Because we notice there are three different midsegments in any triangle. Okay, so that's just what it is. And now this is important because we have a theorem that goes with this that tells me information about more things in the triangle. Okay, so this is the triangle midsegment theorem. And the triangle midsegment theorem says this. I'm going to say if a line is a midsegment of a triangle, if I see that I have a line and if it's a midsegment of a triangle, then what I can say is I can say a couple of things. I can say number one, I'm going to say then it is parallel to one of the sides. So one of my sides of my triangle, it is parallel to one of the sides, and also it is half the length. Half the length of that side. So two things that I know if I see a midsegment. Okay, first thing that I know is I know that it's going to be parallel to one of the sides. And you'll know which one that is because it's the one that it doesn't intersect. Okay, it doesn't cross over with. And then secondly, other than just being parallel to that side, it's also going to be exactly half the length of that side length as well. Okay, so if we're using our example here, if I see MN is a midsegment, for example, okay, first thing that I know, it's parallel to one of the sides, and the side that it has to be parallel to is the one that's not intersecting, so JL. So I would know MN, for example, is parallel to JL. Okay, and then other than that, I also know it's half the length of that side as well. So I would be able to say MN is 1/2 of JL. Okay, these are two things that I know if I'm told that something is a midsegment here. Okay, so very helpful, very important, and I can use that to solve for some different lengths. Okay, all right, so final example here, putting this to use, making sure we understand how this works here. Let's say we're given this triangle, and let's say we're given that XZ and XY are midsegments. So first off, if I want to find XZ, let's look at this here. It is a midsegment, and if I want to find the actual length of it, remember we said it's going to be half the length of the side that it's parallel to. And in this case, the side that it has to be parallel to is RT. So I would say XZ is 1/2 of RT. And I know what RT is, so I can just go ahead and actually plug that in here. I could say XZ is 1/2 of 13, which means here, I can just type that in my calculator. If I don't know, 1/2 of 13 is just 6.5. So XZ equals 6.5 here. Okay, so just using that idea that we just talked about. Okay? All right, next one here that it asked us to find is it asked us to find the length of ST here. So I can look at ST, And remember, I can use the midsegment that it is parallel to. In this case, we were told that xy is a midsegment here, and we know what that is, or we know what that length is. It's going to be 7. So what my equation could look like is the same thing as before. I can say the midsegment is half the length of the side that it's parallel to. So for example, ST. Okay, XY is going to be half of ST. Okay, or another way to think about this, if I kind of rearrange some things in this equation, okay, if I wanted to get rid of the half here, I could just multiply by 2. So another way to think about this is twice the value of xy is just going to be st. Or in other words, st is just going to be twice the length of xy. Okay, another way to think about it. Okay, so in that case, what this means here is I can say st equals 2 times xy, and I know what xy is, that's just 7, so I'll go ahead and plug that in. So st here in this case just equals 14. Okay, so it works in the reverse order as well. If you're given the midsegment, all you have to do is double it to find out what the side length st is. Okay, all right, and then the last one here, putting this to use a little bit more and kind of fully testing our knowledge of this, it's asking us to find the angle measure of RYX. So first off, I'm going to go ahead and just label this here, RYX. Remember, middle letters are vertex here. So it's looking for this angle right here. Okay, and if I want to try to find information about this angle, there are a few different things that I could do. One of the things that I could notice here is, remember, we said if this is a midsegment, if XZ is a midsegment, then it's going to be parallel to this side right here. So for instance, these two, RT and XZ, are parallel. And that's helpful to me because we've talked about a lot of different things that we know about angles in parallel lines. So notice we could draw this to the side if we really needed to. I could draw XZ here and RT. And then notice our transversal that goes through both of them would be XY right here. So now I have these two parallel lines, and this looks a lot like the diagrams that we did last semester when we were dealing with parallel and perpendicular lines. I would say this is 124. This is the angle I'm looking for, and we have a name for these kinds of angles. We call these alternate interior angles, and we always said that alternate interior angles are going to be congruent. So what do I know about this, or what is my final answer going to be? I know that the measure of angle RYX is going to be the same thing as the one up here. So that is going to have to be 124 as well. Okay, so we can use all of this information that we're given. If we see that lines are parallel, we can usually use the things that we've talked about with alternate interior angles and so on and so forth. Okay, so that is the notes for today. Homework assignment that goes with this is 8.3, and that should be posted on the class website, or I'll hand that out to you in class in either case. Okay, and then same as always, if you guys have any questions, feel free to let me know. All right, thanks guys.